name is Paul Girton, and I'm the station manager at Norfolk Community Television Station, right here in Norfolk. Now, I know a lot of us have been into Boston and we've been stuck in traffic like this. It seems like forever. So not too long ago, Jim McNeil and Donna Jones and myself went into Boston to find out what the big deal is about the Big Dig. We decided that we would go in and take a look so that we could come back and let folks know just what's in store for us and what the future will bring. We were fortunate enough to tie up with a fellow by the name of Sean O'Neill. Sean is with the Public Relations Department of the Big Dig, and he took us on a tour that we hope to share with you. So why don't you come along with us right now as we go and get an eagle's eye view, go down into the tunnels of the Big Dig, and stand right there in the middle of the world's largest cable-stayed bridge. Come along with us and enjoy the Big Dig.
Norfolk Public Access here on the Big Dig, ladies and gentlemen. Unbelievable. The representatives of Norfolk Public Television. Excellent.
February 21st, 2001.
Outstanding individuals that are going to be going and climbing and digging and fighting, and I'm going to give them a couple of shovels and a welding torch. We're going to utilize their labor to assist in bringing down the cost of this massive undertaking. So hopefully you guys are ready to work, right?
Oh, yeah.
You sure?
Yes, sir.
All right, good. Let's go. What you're looking at right here is the interchange of I-90 and I-93. That's going to dramatically impact how people access and get through and basically get around the city of Boston. Heading now from east to west will be I-90. Directly in front of us, if you look to your left over here, you can notice there's a train. That's the active commuter rail. And also the Acela train comes in directly to South Station. Right underneath that train is where I-90 is going to continue. I-90 dead ends today immediately to my right, but our future construction and our construction today will continue I-90 straight underneath the railway tracks, straight across the 4-point channel. That's the waterway in front of Gillette. We are building basically an underwater bridge, if you can imagine that, and then we are going straight across through South Boston to connect up with the Ted Williams Tunnel. I-90 basically is going to be a bypass. It'll bypass the city of Boston for everyone coming from the west and also from the south. If you're coming from I-90 out in western Massachusetts, or if you're coming from 95, which feeds into the Southeast Expressway, and you'd like to go to Logan or you'd like to head up to 1A North, off you go, I-90 eastbound. Continue straight through and literally bypass the city. That's going to have a dramatic impact on the situation here in Boston with traffic, because 100,000 vehicles a day will be taking I-90 eastbound, no longer taking the existing central artery corridor. Now, secondary to the I-90, let's talk about I-93. The future I-93 is going to be submerged. It'll be an underground tunnel work. And coming into the city at this point, all traffic for 93 will be elevated, either heading north or heading south. But after this point, you will be underground. Immediately underneath these cars here to our left, if you look straight down, you notice that red truck and that red car there. Directly underneath it, that will be 93 northbound. We'll take you in there in a few moments. You'll be able to see it. 93 northbound will continue straight through the city of Boston, and will come up and out of the city of Boston at the new Leonard P. Zachem Bunker Hill Bridge, which is spanning the Charles River. To our right, the existing entrance and exit from the downtown corridor, which is north and south, today will be southbound only tomorrow. So if you were looking at Boston from an aerial standpoint and the central artery from an aerial standpoint, in the future it'll be a little bit like a wishbone. You'll have a separation of the northbound and southbound. Northbound coming up Atlantic Avenue, right underneath us here to our left, beside South Station. Southbound underneath Chinatown, heading south. After that, they will both tunnel segments will be side by side right after South Station. So right after South Station, both tunnel segments will be side by side. and they will carry through the city of Boston. Actually, we will be going underneath South Station, underneath the red line, and then going all the way up and over the blue line, dipping down again so that the Callahan-Sumner system can connect into us, and then eventually to the new Charles River crossing of the Leonard P. Zakim Bunker Hill Bridge. So literally, the tunnel, if you looked at it linearly, it kind of goes like this, up and down, and finally up again. Makes it a very interesting construction issue. Again, just to finalize this whole area, this is contract 9A4. This is the I-90, I-93 interchange. It is the most complex interchange design to date, and it's extremely difficult from a standpoint of description, but why don't I give it a shot here. At this point, if you're coming from I-90 and you want to head to Logan, you will continue straight across to our left. If you would like to head to Boston from I-90, you will exit off, come up to Surface, or you can go straight onto 93. So that is 3 different alternatives now that you have from I-90 you don't have today. And the same heading west, coming from Logan. If you'd like to go to downtown Boston, you can exit off here and go 93 northbound. If you'd like to go to Chinatown, you can exit off immediately to my right and come up to Surface, where these gentlemen, these men and women are working down there, demolishing an old support wall that we built, which is temporary construction. That'll allow traffic from I-90 heading westbound to head to Chinatown and to Surface. And also there will be another ramp, people coming from I-90 westbound that want to head on to I-93 southbound. So as confusing as all of this description may appear, you can head north, south, east, or west from this central point. And that's what makes this extremely complex, because the interchange itself is something that is on 3 different levels: sub-level, grade level, and above grade. So it's extremely complex, and it's in a very limited space. And at the same time, you have existing interstate traffic on it, which complicates the matter even further. This is a great example of the complexity of this project, but at the same time, it is just a small example of it, believe it or not. If we can look east now towards Logan Airport, it can give you a visualization of exactly how I-90 cuts through South Boston. Slightly over to our right-hand side here, you can see, again, Gillette, and you can see the Fort Point Channel area. That is where we're building that underwater bridge. It'll go right across to the left of Gillette. All of a sudden, you may be able to see the outline of an orange fenced area. That's called the casting basin, referred to as contract 9B1, in which we literally manufacture the tunnel sections, which will be brought into the Fort Point Channel and sunk on top of caissons, and basically cross and span the Fort Point Channel. Once those sections are brought out and laid into place, the casting basin itself goes from being a dry dock to a land-based tunnel. So it goes from being a manufacturing facility to an actual tunnel. And as you can see, you can notice those little dots on the side of the wall. That'll give you the perimeter of the wall and the perimeter of the casting basin. It's 1,000 feet long. It's 325 feet across. It goes down 65 feet. It's bigger than 3 football fields. That will continue I-90. That'll be the land portion now of I-90. We will deck that over. Our tunnel will be underneath. You won't even know we were there. But if you go straight through now, you follow the cranes. If you literally follow the cranes, you can actually see the trajectory of our future I-90 tunnel, because that's exactly where we're constructing our tunnel, in between a fine path cut between those buildings. You notice straight ahead, and then slightly to our left, I don't know if you can see that out in the horizon, that's Logan Airport. Because this tunnel here, which cuts through South Boston, I-90, connects directly to the Ted Williams Tunnel, which brings you directly across Boston Harbor to Logan Airport. And you can see the Logan Towers over to our left by the American flag. That really gives you a perspective on how big this project is. And this is the completion of I-90. I-90 is the only interstate system in the country that is not connected on the East Coast by an actual international airport. Way out in the horizon here, I don't know if you can notice, there's a drumlin to the right of that crane. You see that? That's actually called Spectacle Island. That was an old dump, an old facility that's been out in the harbor for some time now, and we actually capped it, and we placed a lot of excavate on there, and now it is part of the National Park System. It'll be opened up in the next few months, in a year from now. It's a magnificent effect of how the project can really has helped the environment in the Boston and New England community. Underneath us, directly underneath us now, this is 93 northbound. You're looking at cut and covered tunnel, which has been cut and covered. It's done. We will go down in there momentarily, and you'll be able to see exactly how complete it is. But if you notice, straight up, you can see South Station, that kind of pinkish brick building to our right. But that is the work of I-93 northbound heading straight up through the city. Okay, we are looking now at 93 northbound. Heading into the city. If you notice to straight in front of you, those are the railway tracks we were viewing from the aerial view from the top of the building. Now we're going to take you down into 93 northbound. As we swing around here, you'll notice directly in front of us at this point, it's future 93 northbound. And we'll walk in there and we'll give you an understanding of how this actually all comes together. This is called cut and cover tunnel work. Going through Boston is difficult because Boston is primarily historic fill. It means it's very unstable soil. And so to go through Boston, we have to use a tunneling technique called cut and cover. Slurry wall creation for the cut, and then we just deck it over and we excavate as we go. It's devised by the Italians in Italy because of the unstable conditions there, the high water content. That's Boston's unique solution because Boston is not on terra firma. It is not the channel. You cannot bore through bedrock here. You have to actually cut through very unstable soil situations, and that's what made it extremely difficult. There was a lot of unknowns when you go into historic fill because you basically are not aware of what you could run into. All right, we will go down in there next. All right, guys, we're taking you down into 93 northbound. Described earlier as cut and cover tunnel work. Please take a notice, we're actually putting the tile up. The tile finishing, the lighting, the electrical work, the fire apparatus, the rescue issues, the communication networks, everything you could possibly imagine after heavy construction. Heavy construction is now complete. The project all in all is 72% complete. We're at our peak construction right now, which will let you know proudly that this project is on schedule. We will be complete in 2004. But let me give you the milestones, basically the phases as this whole giant map comes together, this whole giant puzzle really comes together. In November of 2002, you will have 93 northbound, which is where we're standing. That'll be open. That means the new bridge will be open. In November 2003, 93 southbound will be open. So there's about a year difference between the north and the south. And that's primarily because people are using the existing infrastructure that we have here in Boston, and you cannot demolish old structure, you cannot replace old structure while people are actually using it. So we have a phase in and phase out. People going north will be able to head north November 2002. And then we can rehab the old Dewey Square Tunnel underneath Chinatown, and that completion will take about 10 to 12 months. So that's why we open up 93 southbound a year later. And that's contract 1786. All right, heading right down here now, you get a real good visual of how massive this project really is. At this point, you're heading down to get underneath the red line. We are heading north through the city of Boston, and the red line system actually heads east-west. So it's coming directly across our trajectory. So the guarantee we don't go head right into it, we're going to go underneath it. So if you look at the grade, I don't know if you can pick it up on the camera, but the grade here is 5%. That's pretty steep. That's 5 feet every 100 feet. Because we need to get down to 120 feet underground so that we can go underneath the red line. But that also means we're going to hold the red line up. And that's what makes another challenging point in this project. Take a look at the new sign postings. We're already putting the signs up. The ventilation system is going in. A lot of work going on here right now. It's part of the AA contract. You are now standing at the main line 93 northbound. All traffic of the future is heading northbound. Right above us, Atlantic Avenue. Intersecting with us, Summer Street, South Station Tunnel, which is the red line. But at this point, if you notice right here, you notice two tunnel segments. To our left is traffic coming from I-90 West and I-90 East. People that are coming from Logan Airport who want to exit off and go to downtown Boston are coming over to our far left here. People that are coming from Framingham, Massachusetts or Western Mass are to the right of that white tunnel opening there. You can't quite discern it, but trust me, mainline I-90 is immediately here to our left, coming into mainline 93. So one of the unique design factors of the project is that you don't have merges. You don't have 6 lanes going down into 3. You actually open up. This opens up to 5 lanes so that you don't have to worry about impact of residual traffic. So now you're standing on I-90 coming in to 93, and this is 93 northbound. And this allows traffic to head straight through the city of Boston northbound, while at the same time, mainline flow of street traffic is right above us. But we're going down to our deepest depth. We're going down to 120 feet because straight across us, South Station. And we'll show you how we hold that whole system up. Okay, what you're looking at here is a slurry wall. And that's the cut part when people talk about a cut and cover tunnel. The slurry wall is literally, the best analogy to give anyone is think of it as a rib cage. We have to create a support mechanism that keeps the outside world from coming in and at the same time being able to work within this zone so we can build our tunnel. The slurry wall was dug in a trench from surface. We just scooped out 1 bucket at a time. And as you scoop out into unstable soil, water comes in. And what happens is it's the equivalent of digging at the beach. When you dig a trench at the beach or you dig a hole in the beach, water comes in and it collapses in on you. Exact same problem here in Boston. So as we dug down into the earth, we filled that trench with a composite material called slurry. And that material, slurry, is made up of clay and water, bentonite clay and water. Or in its synthetic form, polymer slurry, which is polymer and water. And all that does is like a pea soup. As you dig the trench, we replace the excavate with slurry, like a shake. And that allows the trench to stay open so that it won't continually collapse in on us. And that's what makes it very complicated, because as we're going down and digging, this trench cut here goes down 120 feet. Now, once that trench is dug, then what we do is, it's full with slurry now, so it's dug and full with slurry. We put in I-beams, individual ribs, 5 to 6 feet on center. Some areas were 3 feet on center. That means lined up, just like your rib cage. That allows us then to pour in concrete from the top. We have a tremie pipe system that goes in between the ribs like a straw, goes right down through the slurry, and then from the top, from outside, from surface, we have concrete trucks dumping in and funneling right down through this giant straw. It's called a tremie pipe. Spills out at the base of the trench. Now, concrete has a much higher density compared to the slurry, so what does it do? It displaces it. It actually pushes the slurry up, and we take the slurry out, and we literally just built a giant concrete wall. And that's exactly what's behind us. That is what's called your slurry wall. So you have a slurry wall to your right and a slurry wall to your left, and then you can literally remove all the earth in between. But as you go down and remove all the earth in between, you have to put in temporary support structures. Struts is what they are called, all the way down so that you can start to begin your foundation. What we're standing on here is the foundation of I-93 Tunnel Box 93 northbound. This foundation is 18 feet thick of concrete. That constitutes an excellent foundation and also a strut. So now the rib cage has a backbone. That's very important, because then you can remove all the temporary struts that you put in on your way down. You can remove them now so that you've created a nice box shape, and you can see it here. And then you put your finishing girders up on top, basically your roof, and you've built a cut and cover tunnel. That's 93 northbound, and that's basically how we built 93 southbound also. It's called cut and cover tunnel work. All right, take your right underneath South Station. All right, at this point, 93 northbound, we are at our deepest segment. This is 120 feet underground. And the reason for that is because we had to tunnel underneath the Red Line system and South Station. If you can notice here, there's a finishing struts here, the finishing I-beams above us. All of a sudden it stops. The gray area stops and it becomes concrete. Now that concrete is part of a support structure that we built underneath South Station to hold it up. Best analogy is we're cutting through Boston. We talked about the slurry walls, how we're cutting through the city. Now you can't cut through the Red Line because it's part of support structure for South Station and everything else. So what we do is we stop our cut and cover tunnel work. We go beyond South Station, we mine down an eastern shaft and a western shaft, we mine down, and then we mine underneath. And at that point, we start building a drift wall system. A drift wall system is a column support structure that's built underground, but instead of being vertical and at grade, just like a regular old Coliseum, they're horizontal and underground. In this case, they're down 120 feet. So imagine here where my thumb represents a mining shaft from surface straight down. And then we mine south. Mine down and mine south, down and south, down and south. And then we fill in each individual finger. It's a mining shaft at first, but then we fill it in with concrete. So that becomes a support structure, and you do it again for your other hand. Excuse the bad analogy here, but it really works well. And that is how you hold up South Station, like that. Okay? See that? Yeah, I understand. But that's literally how we have to do it, because we can't cut through it. That's what's going on right here. All right. Think that's good and noisy for you? Okay, we're basically on the old elevated artery, which will be replaced by the future 93 north and southbound tunnel. And we're going to take you right up onto the bridge, give you a good visual. But you can see it on the horizon now, the cable-stayed bridge. It's the widest asymmetrical cable-stayed bridge in the world. It's an A-frame supported structure. You can notice the legs are like the letter A, capital letter A, and the cables themselves are part of the support mechanism that are actually tied into the tower and into the legs, and will hold up the actual bridge. Back again with Norfolk Public Access Television. We're actually on the brand new asymmetrical cable-stayed bridge called the Leonard P. Zachem Bunker Hill Bridge here in Boston. This is spanning the Charles River. It is 10 lanes wide, 4 lanes north and 4 lanes south. We are actually standing on the future 4 lanes south. To the right of these cables is the 4 lanes north. Now I did say 10, so that means we're missing 2. That's 8 in total underneath the legs here. We have 2 additional lanes northbound cantilevered off to the east of the right leg. And that is going to be for a main ramp connection from the north end of Boston and also from the Callahan-Sumner system to come right up here. You have to think of it this way. The bridge itself is at the northernmost point of the tunnel, and the north end happens to be at the northernmost point of mainline Boston. So you don't want people from the north end merging in directly with the northbound tunnel because of congestion issues and traffic management issues. This way, you solve that problem by creating the 2 additional lanes off to the east, bringing us straight through. Something that should be said about this structure, it's an awesome looking structure, but it's extremely high tech. It's the footprint that makes it difficult to build, because we actually have the old infrastructure here in Boston and we had to place this bridge right within it. Look at the tower. This spires here is it's a replica of the Bunker Hill Monument because it is an obelisk, but at the same time the cables themselves are tied into it. Basically, the way you hold this structure up are the cables. They are tied into the spire and the legs, and then they tie back into the base platform, which is right what we're standing on. It's a giant balancing act, which one structure supports the other, and the cables connect both. The cable lines themselves, if you look at these pipes, you can see them from the highway when you're driving, but it's actually the lower base here is a steel anti-vandalism protection line. Basically for vehicles that bang into it or what have you, there will be a barrier wall here. But above us, you have a high polyethylene sheet, which is continuous. There's no break in it, so it will allow for less corrosive materials to get in there, i.e. water, because it's continuous. There's a little ribbing on that. You can see that. That's so that the rain will roll down it. You don't want big sheets of rain or ice getting caught up on these actual cables and falling down in sheets. And also you don't want it on there because it'll cause the cables with high wind to maybe start a little movement. You're looking at the outer shell of a massively complex cable system. This cable, inside it contains many smaller cables. Based on the amount of weight that this actual cable would have to hold up, varies to the size of the actual cable itself. The best way to explain this is that the further up we go, the closer we get to the legs, the less individual cables are in these pipes. The further back we go, which is where we're standing, there is a greater amount of individual cables. The furthest one is 78. And it looks like a honeycomb. Individual cables strung through this honeycomb-like device, which actually locks them into place because you have a wedging system in there. And that, it's almost, you know, the finger, kind of a finger torture device. You know how you get your finger trapped when you were a kid? Think of it that way. The actual counterbalancing of the force, the cable trying to pull out versus the actual wedging mechanism that wants to pull it, you know, it tensions itself. And that's how we hold everything into place. Jump up and down and see if it can hold us. Ready? Look at that. We know what we're building. That's pretty good. This structure is going to be able to handle a lot of traffic. Okay, so it's going to take, you're standing on 93 southbound. So basically you'll be driving from the north, heading south through Boston. And at this point you'll be up next to the Fleet Center. Remember now, this giant green structure, the old elevated artery, is going to be gone. Then you'll be going underground and you go right through Boston. Does it make sense?
Yep,
okay.
Perfect.
What's
You're going to have 5 each way, right?
No, actually, we're going to have four southbound, 4 northbound, and then 2 additional northbound.
Oh, okay.
So technically 6 northbound total, 4 southbound. And that's what makes this bridge unique, because it's asymmetrical. It's not symmetrical. The balancing act that we talk about. Because if you guys weigh the same, I have no problem. I can hold you both up equally. But if somebody weighs a little bit more, there's more I have to hold up. So that's why the balancing act here, the cables are so unique, because they actually counteract, they counterbalance itself.
Okay.
All right? That's what makes it one of the most unique structures in the world. It's not that long of a structure, but it's extremely wide.
So in other words, all the cables come up these pipes.
Correct. These pipes are, again, they're polyethylene sheets that are there for protection from corrosion, etc. And then there's individual cables inside there that are also actually wrapped in a polyethylene kind of plastic. Polyethylene is a high-density plastic. And these individual cables that are in there, it's the equivalent of a big bound rope. You know, if you look at a big old sailor's rope, and it's a piece of rope wound within a piece of rope, wound within a piece of rope, that's a big piece of rope. Exact same concept here. All right, with the cable. And then the individual cables are tied into a locking, basically a braking mechanism, bracing mechanism that allow them to lock into place. And you can see those underneath when we go back down. Any other questions you might have?
How do you estimate the weight the bridge can hold when you don't know what the vehicles are carrying that come over it?
Excellent question. Believe it or not, a bridge like this, or any bridge for that matter, it has a higher problem dealing with people standing close together. If there was thousands of people on this bridge, all right, all standing close together, structurally, that has a greater variance on the structure's capabilities to hold it up than would be a rolling vehicle.
Oh, really?
Because a rolling vehicle displaces the weight on the tires, you see, and it separates it. Now, the way you can judge how much a structure can hold is based on the mathematical principles about how much the actual cables can support via the concrete foundation, and then you displace all that weight per square, you know, per the measurement of the actual structure, and that's how you can decide. It's basically a computer model. This whole bridge was designed using a computer model structure so that we could therefore calculate how much or how big we have to make it so that it can hold X amount of traffic. But you're almost better off building a bridge solely for traffic purposes than you would be a footbridge. I don't know if you remember the rededication of the San Francisco Golden Gate Bridge a few years ago. They had a walking, they invited thousands and thousands and thousands of people onto it. They're all on it at one time, and it would actually cause the bridge to sag a little bit because it's per square inch. You know, pounds per square inch, PSIs, is really what it breaks down to. So when people are all huddled together, you know, we're taking up a little bit of space here, but yet, you know, so think of it that way. So vehicles can actually handle that. You're almost better off using vehicles on a bridge than anything else.
Yeah,
because they displace. They displace the weight on their tires.
That's why spread it out.
Spread it out, exactly. So this structure will be able to handle plenty of weight. If you look up here, the old bridge, the old double-decker, was completed in 1959, has done a magnificent job because it wasn't designed to do what it's doing. It was designed to take about 75,000 vehicles a day into and out of the city of Boston, ended up having to take 190,000. So it's the equivalent of a 130-pound person having to, you know, bench press to, you know, 300 pounds every day. So the craftsmanship and the work ethic gone into that structure has been outstanding. But its time has come and we have to replace it. So one point we got to make here on the Big Dig is that you have to understand the infrastructure here in Boston has aged. It's reached its capacity. If we did not take this project into consideration and do it, what would you do? Replace the old problem? And that dollar amount would be approximately $7.5 to $8.5 billion just to replace what you have, because you can't structurally leave it. So this is an issue that a lot of American cities are going to have to deal with, replacing a lot of their old infrastructure. And much like the old Bunker Hill Monument across the river here signifies a revolution, we're taking on another one here in infrastructure in Boston. So pretty neat. Come on up here, walk to the edge. You said you needed to get, because of the growth in Norfolk, you needed to work on mainline connections to sewer and services and things like that.
Correct.
So there will be a lot of work going on there. I mean, obviously nothing on this scale. This is the largest civil works project in the country's history.
Oh, yeah.
Civil engineering project in the country's
bet.
history. And it's happening in the oldest city, one of the oldest cities in the country. So this is a great project for the entire Commonwealth, because a great proportion of the commerce from the Commonwealth comes within the parameters of this metropolitan district. So people in Norfolk will benefit because businesses that are here will stay here, but they will have satellite offices in Western Mass and Southwestern Mass, things like that. And you see that happening. I mean, look at the expansion of 495.
Yep.
That's had great effect on your community. You know, it's the new 128 basically. So this as long as, you know, everyone's benefiting from this project, which they are, I think we're in good stead, and you're actually seeing where your money is going. We have the RE, the gentleman in charge of this wonderful structure. His name is Al McPhail, and he'll let us know exactly how they're coming along. Al, how's your bridge doing today?
Well, not bad. We only have, after today, we'll only have 4 more pairs of cables to go in on the north side there before we get to the center. And we plan to make the closure in the middle of the river about early April, and that's not an instantaneous thing, you know. It'll be done over a little period of time. But then after that, all that remains to be done is the barriers, the traffic barriers, and the overlay, the running surface. Here now, you see that we just have one more set of edge girders to go in, and then there's a little 8-foot closure section, and we plan to make this closure in early April, sort of thing. This crane that you see in front of you here, this is on flexi floats, and you see as we close, we can't really reach with that crane. We have to back it out, and that gets a little tricky, and we have to flatten down the gantry and flatten down the booms to move it back and forth underneath the bridge once the steel is in place.
Excellent question earlier on. How can you tell how much weight a structure like this can hold? Like, how do you break down the weight variables on the individual cables, that sort of thing? Or, do you know what you can do?
Well, it's, it's quite fancy calculations, but they do it all with computers now and a computerized model, and that you know, simplifies the whole thing. But the original model to run to check through on various situations, it took a long time, like 24 hours of computer time to run the thing. But they do have a better program now that will run it in an hour or two. But to every situation that we're in as the construction goes along, we have a model that a situation that tells us exactly what elevation we should be at, what angle we should be at, and even the towers, any movement in the towers. So it's been pretty well engineered, you know, right from start to finish.
Great.
All right, here we are, the great bridge builders from Norfolk, and as you can see, it took us a couple of weeks to string up all these lines. We want to thank Sean O'Neill at the Big Dig for taking us around today. As you can see, we've seen quite a little bit of the Big Dig and the progress that it's made over the last 7 or 8 years. We're standing now on the bridge that will be in operation in about a year or so, and we'll be able to drive by this bridge pretty soon and be able to say that we stood right here on the middle of the bridge and as it was being made. And we're very thankful, and we want to make a point of saying that we had great cooperation and friendship in making this tape so we could bring it to everybody in Norfolk. So thank you very much.
Sean, thank you very much.
Oh, you're welcome, guys.
Thank you.
Well, I certainly hope that you enjoyed that. We certainly did. It was kind of a cool day, but we learned an awful lot. And at the end of this program, we're going to show you a couple more minutes of some great scenes in and around the Big Dig. But I just wanted to take a couple of minutes to just give you an idea of some of the really fun facts about the Big Dig. For instance, that by the time the Big Dig underground central artery opens completely in the year 2010, it will carry about 245,000 vehicles a day, and that the Ted Williams Tunnel itself will carry about 94,000 vehicles. Interesting thing about the dirt that's been dug up by the Big Dig. The project will excavate a total of 13 million cubic yards of dirt. Now that's enough to fill Foxborough Stadium 13 times, rim to rim. That's pretty interesting. Another thing is that the project will place 3.8 million cubic yards of concrete. Now just imagine that. That's enough concrete to build a sidewalk 3 feet wide and 4 inches thick from Boston to San Francisco and back 3 times. That's an awful lot of concrete. The reinforcing steel used in the project would make a 1-inch steel bar long enough to wrap around the Earth at the equator. And when the project finally tears down the elevated central artery, right where the bridge here is going to go, starting in 2002, it will remove enough structural steel to make 5 of the Tobin bridges, the bridges that were there. And the project's 7-building ventilation system will be the largest highway tunnel vent system in the entire world. The cable-stayed bridge, the one that we're looking at right here, this beautiful bridge that we were on just a few minutes ago, will use 1,820 miles of steel wire to form the 7 wire strands that are in turn bound together to form all the support cables, the largest a whole foot in diameter. And just a final couple of notes. Right now, there are, in all of the Big Dig and all the areas that we saw from the rooftops and everything, we could see about 150 cranes that are in use today. Well, we want to thank you for coming along on our tour with us. And just as a final little treat, we're going to show you some of what we thought were some of the most interesting sights, the most interesting views for the next couple of minutes with hopefully some music that will go along with it. So thank you for coming along with us. We thank very much Mr. Sean O'Neill from the Big Dig, who took us around and gave us an absolutely wonderful tour. So this is Paul Girton for NCTV saying so long and see you down at the Big Dig.